Okay, so the title I have chosen for this particular session, I have slightly reframed it and I have considered it as differential equations in fluid dynamics. Okay, as the broad topic of this particular workshop is actually related
Sir,
to differential equations, and fluid dynamics is one of the important application. Here differential equations are very important. Okay, whatever the phenomena we are having in fluids, and if we want to study it, then obviously the governing equations which control that particular phenomena from our theoretical background, theoretical understanding of the fluids, these governing equations are of differential nature only. So we are having differential equations as the main governing equations for fluid dynamics problems, and we have to do the solution of these governing equations in order to study the behavior or characteristics of our systems. Okay, so wherever like we find the scope of fluids, we can say every situation where fluids are present, we can say indirectly differential equations are present. Okay, so you can see that like in this particular slide, now I'll show some of the areas or some of the branches of the pure science where we can find occurrences of the fluids. So you can see the occurrences of fluids in pure sciences. So if we talk about atmospheric sciences, we are having global circulations, long range weather predictions, etc., climate change. Then we are having oceanography, where we are having waves on the surface of the ocean. Okay, geophysics. Then we are having astrophysics, biological sciences. For example, inside our body also, our heart is actually pumping blood, which is a typical type of non-Newtonian fluid. Then we are having arteries in our body where these are nothing but acting as the pipe for the flow of blood. So it means the occurrences of fluid dynamics are there in wide range of applications. Apart from that, we are having significant number of applications in industry as well as in engineering where we are having the occurrence of fluids. For example, if we talk about automobiles, so generally in our car or trucks, etc., we are having IC engines, internal combustion engines, where we provide the energy from the fuel, and that energy is actually converted into mechanical energy with the help of some arrangement, some device. That particular device is known as internal combustion engine, and inside that engine actually we are having flow of air and fuel. Okay, so what air is nothing but a fluid. Fuel also we are having petrol, diesel as our main fuels for our vehicle. So we can say that that is also a liquid, that is also a fluid. Okay, then in our aeroplanes, turbojet engines are there. Water disposal systems, for example, chemical treatment plant, sewage treatment plant, then pollution dispersion. So you can see that from the power plants, we are having long chimneys from where our exhaust gases enters into the surroundings. Then we are having steam turbines, gas turbines, from where actually we get our electricity, whatever we are using in our home applications as well as the uh, offices, industrial systems for obtaining energy. Then we are having pipelines where we transport the crude oil and natural oil. We are having many applications where we are having the fluid structure interactions. We are having heating, ventilation, and air conditioning systems in our home as well as office appliances. So all these involves the occurrences of fluids, cooling systems, solar heating systems, artificial hearts, kidney, etc. Okay, so there are many manufacturing processes. For example, if we have to do the painting on automobile, there will be spray paints which will be providing a layer of paint coating over the surfaces. Okay, so it means from this particular these particular two slides, you can see that we are having wide occurrences of the fluids, and wherever we are having occurrence of the fluid, we will be having the presence of differential equations. Differential equation obviously is not present in the physical form, but it is there in the hidden form, which is basically specifying the governing equations for particular phenomenon which is happening. And if we have to study the dynamics or characteristics of our engineering system, obviously we have to solve differential equations and we have to characterize that system. Okay. Now, in this particular slide, I would like to make a difference in between a solid and a fluid. So, for example, if we are having a steel block, and let us consider that this steel block is subjected to some sort of force. Okay, so this particular force, if it is applied parallel to the face of any fluid, then this is something we call as shear stress. And if any force which is applied in a direction perpendicular to that of the plane of the object, that particular stress we call as normal stress. And if anything which is parallel to the plane, that we call as nothing but shear stress. Okay, so what I am considering, that I have one solid object, one steel object, and this object is subjected to shear stress. So obviously, if I will be applying shear stress, I will be finally finding that this will be slightly deforming like this. Okay, so this is our original block. When it is subjected to shear stress, we will be finding that our final block will be something like this. Okay, so for example, this was its original position, so it has distorted through an angle delta theta upon the application of this shear stress. Okay, so this is the case of a typical solid where we are having nothing but finite deformation of our solid element when we are subjecting it to shear stress. On the other hand, if we take a water column and if we subject this water column to once again the same set of shear stress, what we will be finding that in this particular case we will be having basically continuous deformation. For example, if I say that at an instant t1 I have delta theta 1 distortion. If I change the time to t2, which is greater than t1, in that case what will be happening? I will be having more deformation. At some other time t3 I will be having more deformation. So it means in case of solid, what was happening, tau was actually leading to some finite deformation delta theta. However, in case of fluid, what we will be having, upon the inclusion of the shear stress, we will be having continuous deformation of the fluid element. Okay, so I can say that nothing but tau will be having dependence on del theta by del t, because whatever the deformation we are getting, that is continuous and that is increasing with time. So that's why while we are talking about the fluids, we say that the shear stress is actually changing the, or continuously changing the deformation of the fluid element. So that's why we are writing it with rate of change of deformation. Okay. Now, what we want to do, one thing we have understood, that in case of fluids, we are having tau is proportional to del theta by del t. Means when we are applying some shear stress, that is actually causing our fluid element to continuously deform with time. Okay, but whether this deformation in between the two is linear or non-linear, how it will be changing, that is something which is decided by the type of the fluid. Okay. So over here what we are having once again a same type of control element I have considered, and I have considered that the bottom face of this fluid element is having zero velocity and the top face of this fluid element is having some u velocity. Okay, so because of that, obviously what will be happening, we will be having nothing but continuous deformation. So at any instant I have considered that we are having delta theta as nothing but our deformation. Okay, so now here what we are having, as I already told you, that tau shear stress will be proportional to rate of shear strain, so del theta by del T, but whether this relationship will be linear, non-linear, so that is something which is decided by the type of the fluid. So if this relationship between tau and delta T is linear, then we call that particular type of fluid as nothing but Newtonian fluid. Okay. So if our relation is linear, if we want to convert this proportionality into equality, we will be finding tau equal to some constant times del theta by del t. So that particular constant is something which is called as viscosity, or in more general term, I can call it as dynamic viscosity of the fluid medium. Okay. So now the relationship in between tau and del theta by del t will be remaining linear if value of this dynamic viscosity is constant. So if we are having a fluid for which dynamic viscosity is constant, that particular type of fluid is something which is known as Newtonian fluid. And any fluid if we are having which is not having constant value of this particular constant which is given over here and which is called as dynamic viscosity, in that case what will be happening, we will be having non-linear dependence between shear stress and del theta by del t. So what I have done, d theta by dt I have plotted over here along uh, abscissa, and tau I have considered along the ordinate. Okay, so we are having one linear line that is particularly applicable for Newtonian fluid, and for that case we can say that our dynamic viscosity is constant. Okay, then we are having certain fluids for which what happens, as we will be having the deformation of the fluid, with the deformation value of this constant will be actually decreasing. So you can see, for example, initially our curve was going something like this, and then as we are moving towards the higher value of d theta by dt, at that time what is basically happening, our value of this constant mu is decreasing. So this particular type of fluids are known as shear thinning fluids. Okay. The meaning of shear thinning fluid is that when rate of shear strain is actually increasing, at that time viscosity of the fluid is actually decreasing. Okay. And these are also known as pseudoplastic fluids. Then we are having some fluids which are known as dilatant fluids. So in case of dilatant fluids, what happens? These particular fluids are known as shear thickening fluids. So for these particular fluids, what will be happening? When shear rate will be increasing, with increase of shear rate, there will be increase in viscosity. Okay. And there are certain fluids for which what happens? These initially will be acting like solids, that you are subjecting that fluid to large amount of shear stress, but you will not be finding any type of deformation. So it means the initial characteristics are like solid. Okay. But if you subject to up to certain minimum amount of stress, and that particular stress is known as yield stress, if you increase value of stress above the yield stress, in that case there will be deformation in these particular type of fluids. Okay, so our toothpaste is a typical example of ideal Bingham plastic fluid. So for example, when we take out toothpaste out of tube, so what we have to do, we need to press. So it means we are providing some yield stress initially, and because of that actually it is coming out of the tube. Okay, now if we are having any fluid for which value of mu is equal to 0, value of viscosity is equal to 0, in that case what will be happening? At zero shear stress also we will be finding that we will be having large deformation of that particular fluid. Okay, so any fluid with zero viscosity is particularly known as ideal fluid, and the corresponding flow condition is known as ideal flow. Okay, now one illustration I have included over here. So you can see we are having some sand and water mixture, and one person is actually draining inside that sand and water mixture. Okay, so you can see what he is saying. Help! I fell into a dilatant fluid. Okay, so he is not saying that he is actually stuck inside mud. Rather, he is saying I fell into a dilatant fluid. Okay, now the person who is outside, who is listening to him, he is actually just thinking that, okay, what he is particularly referring to as dilatant fluid. And because this person who is actually falling inside, he is an engineer, because of that only he is calling it as dilatant fluid. Now, outside person also, if he is an engineer, he will be immediately able to think that he means he is saying quicksand, because quicksand is an example of dilatant fluid. So one photograph also I have included over here. If you find any sand and close to that, if you find some water is there, you will be finding that if you slowly move over that, you can easily walk. Okay. However, if you start moving fast over that mixture, by moving fast, you are nothing but subjecting that particular sand water mixture to the large shear rates. Okay, so at large shear rates, what will be happening? Its viscosity will be increasing, and once its viscosity has increased, it will try to pull your leg into it. Okay, so that is one typical illustration of dilatant fluid I have shown you over here. Apart from that, if we talk about general examples of the fluids which we see in our everyday life, so air, water, kerosene oil, petrol, diesel, all these are the examples of Newtonian fluids. Then we are having some other fluids, for example, blood which is flowing into our body, that is actually type of a typical non-Newtonian fluid. Okay, so this is like overall introduction about different types of the fluids. Now, one important condition which is applicable to a majority of the fluid types, if we are studying or observing our phenomenon under the assumption of continuum, we call that typical condition as nothing but no slip condition. Okay, the meaning of no slip condition is that if we are having interaction in between a fluid and any other object, so what fluid will be doing? Fluid will be immediately try to attain the velocity equal to that of the object in its immediate vicinity. Okay, so one typical illustration I have included over here. I have two plates. So one bottom plate which is fixed. So for this particular bottom plate, we are having 0 as velocity, and we are having one more top plate, and we are subjecting this top plate to some amount of force F, and because of that amount of force F, it is moving with velocity u towards the right. Okay, we are having h as the spacing between these two plates, and we are having some fluid element over here. So you can see that we are having whatever the object, whatever the fluid element, fluid molecule we will be having close to this surface, that particular fluid element will be having 0 velocity, and whatever the fluid element will be there with close to the moving plate, that will be having actually velocity equal to that of the this moving plate velocity. So this is very important boundary conditions which is applicable while we study different type of fluidic phenomenon, particularly under the condition of continuum. Okay, so here what will be happening if I draw the velocity profile at any location. So for example, if I take any location over here I have considered, so at this particular location, what will be happening? At this lowest point, we will be having 0 velocity. At the highest point, we will be having velocity equal to that of u. And in between, because of the viscosity of the fluid, we will be having actually changes value of velocity in between 0 and u. Okay, and we will be having the development of a velocity profile, and this particular velocity profile, whatever is shown over here, we will be getting once the flow is becoming or reaching to the fully developed flow situation. Okay, so below I have included one illustration to depict that why we get 0 velocity or we get velocity of the fluid equal to that of velocity of the surface. Okay, so generally when we look a surface from our naked eye, it may look to us that it's smooth. But if we try to look this surface from the microscopic point of view, we will be finding large number of deformations over that, and these deformations will be of the micrometric size. So obviously the length scale of these deformation or irregularities, whatever we will be finding on the surface, these will be of micrometric size. And what will be happening, because now fluid is over the surface, so some parcels of the fluids will be trapped within these irregularities. So because of that fluid layer which is there in immediate vicinity of this surface, it will be actually reaching velocity equal to that of this surface velocity. If surface is at zero velocity, it will be getting the zero velocity value. Okay. Now, this is one typical representation I have shown over here for the diffusion of momentum. So, I have taken the example that bottom plate is fixed and top plate is actually moving. So, the instant at which we supply the velocity to top plate, what will be happening? We will be finding that and immediately when t is actually approaching to t naught, where t naught is the instant at which actually we have given the velocity u to plate. Okay. So at this particular situation, what will be happening? Only the fluid layer which is there in immediate vicinity with the plate, that will start moving. And as the time will be progressing to some value t1, once again that t1 is not large, it is approaching to t naught only, but it is slightly greater than this particular time instant t dash. Okay, so here slowly you will be finding that velocity will start diffusing in the downward direction to the other fluid layers. Okay, and once the situation is becoming fully developed, once we are getting fully developed flow situation, corresponding to that, we will be finding that top layer is having velocity equal to u, bottom layer is at 0, and in between we will be having some velocity profile. Okay, and obviously whatever the rate or whatever the type of velocity profile we will be finding, that is something which will be controlled by the coefficient or constant which I have considered in the previous slide. That particular constant is known as mu, viscosity of the fluid. So it will be a controlling parameter for what type of velocity profile we will be getting in any physical situation. Okay. Now, when we talk about the fluids, so unlike solids, we are having more complicated equations for characterizing the flow of the fluids. Okay. So in case of solids, what we are having, for example, if I want to study the granular flow situation. Okay. So what I will be having? I will be having some fixed number of particles, say n number of particles. For each and every particle, because it's a solid particle, so it will not be deforming in size. Okay, and moreover, it will not be splitting further into more number of particles. Okay, so obviously, if we are able to keep a track of the n number, we will be easily able to serve the mass conservation condition. So mass will be conserved. However, and apart from that, if we have to study the dynamics of the particles, only we need to apply Newton's second law. We need to do F is equal to mass into acceleration. So we need to find that what are the forces which are acting on this particle, its mass times acceleration, and we will be easily able to study the characteristics or behavior of the particle in a flow field. Okay. However, if we are having a fluid, so what will be happening? For example, if I take pipe, if say some air is flowing through this pipe, okay. So what will be happening now? Because fluid is a completely deformable substance. At the same point of time, it can easily escape through any of the openings which are provided for it. Okay. So it means if we are taking any control volume, if we have to define the conservation of mass for this particular control volume, we have to actually consider that what inflow of the fluid we are sending, what outflow of fluid is actually happening from this, and we will be finding that m inflow minus m outflow will be equal to nothing but dm by dt this will be representing the rate at which there will be change in mass of the control volume. Okay. So this will be a mass conservation equation which will be very, very important while we are studying the characteristics of any fluid control volume. So if we just, I will not go into detailed derivation of this equation, but if we just apply this particular main governing equation for our control volume involving flow of fluid, we will be finding our governing equation for conservation of mass of fluid as something like this, del rho by del T, where rho is one typical property of the fluid which is known as its density, plus del by del x of rho u, del by del y of rho b, del by del z of rho w equal to 0. Okay. Similarly, apart from that, what we have to do when we are having the flow of the fluid, obviously, if we have to find out the flow dynamics, we need to determine the detailed velocity field of the fluid medium. Okay. So for doing that, once again, we will be applying our Newton's second law, which is equal to mass into acceleration. Force is equal to mass into acceleration. Okay. So in case of fluid medium, we are having actually two types of acceleration. One will be del V by del T. Okay, so this particular acceleration is something which is known as local acceleration. It means this will be representing that at any fixed location, how our velocity field is actually changing with time. Okay. Another important acceleration we will be having, particularly in case of flow of fluid, so that will be u times del v by del x. Say if I am writing this particularly for velocity v, and plus v times del v by del y plus w times del v by del z. Here, what I am considering that if I have Cartesian coordinate system x, y and z, I am considering that u, v and w are the velocities along x, y and z direction, and in this particular equation, whatever the acceleration I am writing for the fluid, this acceleration is nothing but in the y direction. Okay, so this is for v velocity. So in case of fluid, apart from local acceleration, we will be having acceleration because of the convection of the fluid medium. Okay, so because of that, what we will be finding that our mass into acceleration term, we will be having del by del T. So this rho is also coming over here. Rho is coming in order to account for the mass. Okay, and this particular part is actually because of the convective acceleration because of flow of fluid. And this first term is at any fixed location with time how much change is there, okay, in the velocity. So what I am doing over here, because velocity is nothing but a vector quantity, so we will be having, if I take Cartesian coordinate system, I will be having three components of velocity, u, v, w. So what I have to do, I have to write three different balance equations based on Newton's second law. One will be in x direction, another will be in y direction, and third will be in z direction. Okay, so this left part of each equation represents the mass into acceleration component. Okay, and in the right side we are having different type of forces which are acting over the fluid element. The first force which I have considered, this is actually known as body force. So mainly in case of our phenomenon which are happening in our atmosphere, gravitational force is actually one of the body force which acts on the fluid. Apart from that, we are having a few more forces which I have written as sigma xx, sigma yx, sigma zx. Okay, so these forces are nothing but this particular first term represents normal stress. So I have already told you that normal stress is something which acts on the fluid element in direction normal to its surface, and these two, sigma yx and sigma zx, represents the terms because of the shear stresses. It means forces which are acting parallel to the fluid element. Okay, so similarly we are having one conservation equation for y momentum and conservation equation for z momentum. So it means you can see that if we have to study the flow of fluid, how complicated is the phenomena. We are having number of equations, we are having number of variables involved over here. So whatever the equations I have included in this particular slide, these are applicable for each and every type of the fluid, because I have included this stress term in generalized form. So that's why this particular equation is actually applicable for all types of fluid. And if we have to apply this equation for a specific type of fluid medium, then obviously what we need to do, we need to apply the corresponding formulation for stress. Okay. So now we are having very famous equations for the fluids. That particular equation is known as Navier-Stokes equation. Navier-Stokes equations comes after we substitute the conditions for Newtonian fluids. Okay. So if we supply the condition for Newtonian fluids, whatever the equation we will be getting, that we call as nothing but Navier-Stokes equation. So I have already told you in our previous slide that we will be having linear relationship in between tau and d theta by dt, particularly for the Newtonian fluids. Okay, so whatever this sigma term I have represented over here, so this is a second order tensor. This sigma is having actually 9 components, and it consists of 2 parts. The very first part includes normal stresses, and these particular normal stresses, actually we are having P as a constant value. So this particular P value is something which is known as hydrostatic pressure. Okay. So this P over here is nothing but hydrostatic pressure, and then we will be having few stresses because of the viscosity of the fluid medium, which will be relating the relationship in between stress and rate of deformation of the fluid medium. So particularly for Newtonian fluids, we are having this as matrix for second order tensor, representing the value of different normal and shear stresses which are occurring because of the viscosity. Now you can clearly see we are having linear relationship in between tau and the deformation, because this mu, whatever we are considering over here, it's actually a constant. Now if we substitute this particular formulation into our main governing equation, and if we consider that our rho is constant, so if density of a fluid is constant, we specify that type of fluid as nothing but incompressible. Okay, for example, water we are having, if we are having water in glass or in a container, then irrespective of the amount of force we are putting on that container, we will be finding that water will always be having almost same density. So the fluid which actually are having this particular type of nature, these are known as incompressible fluid. So obviously incompressible is not inherent characteristic of the fluid, rather this is something which is controlled by the conditions under which fluid is subjected. A same fluid, for example, air in our atmosphere is considered as incompressible, whereas if we take the air at slightly high pressures, we will be finding it of compressible nature. Okay. So if we apply these two conditions, that rho is constant and whatever the stresses I have shown in the previous slide, if we substitute these conditions, finally we will be finding our governing equation for mass conservation as something like this, or in more shorter form, I can write it as that divergence of u vector equal to 0, where my u vector is nothing but u I cap plus v j cap plus w k cap. Okay, so similarly I have x momentum equation. So you can see now in place of sigma we have now got the formulation in terms of viscosity into the velocity gradients. Similarly we have equation for y momentum, similarly we have equation for z momentum. Now in this particular situation, you can see that if we have to study the characteristics of any system involving fluid, we have to solve 3 momentum equations, and plus we have to solve one more equation as nothing but our continuity equation. Okay. and we are having our unknown parameters as u, v, w, and p. So these are our nothing but unknown parameters. Okay. Now we are having some advantage with the help of few mathematical functions which are particularly known as stream function and potential function, and these functions actually helps us in minimizing the number of equations and number of constants whatever we will be using. Okay, the very first function is known as stream function. It is represented by a symbol psi. So we have u as nothing but equal to del psi by del y, and v as nothing but equal to minus del psi by del x. So if I use these replacements to my two-dimensional continuity equation, so if I consider that my flow is two-dimensional only, then obviously I will be considering only del u by del x plus del v by del y equal to 0, and third term del v by del z I will be neglecting. Okay, for a two-dimensional flow situation. So there what will be happening if I use the substitution of x and u and v in terms of psi, we will be having del square psi divided by del x del y minus of del square psi by del x del y. So it means if you are using this particular substitution, what is happening? Our continuity equation is inherently satisfied. So it means we need not to solve this equation. Okay, and at the same point of time, one additional advantage we are getting, that both my different components of velocity u and v are now accounted into a single variable psi. Okay, so now if I substitute this formulation to my x and y momentum equations, there also I'll be finding that my equation will be of two-dimensional nature, and I'll be having only psi and p as the unknown quantities. Okay, another type of function which is a scalar function, that is something which is known as potential function. Okay, so this particular function basically employs the mathematical condition. Okay, so we are having certain flow situation where curl of the velocity vector is equal to 0. So if curl of any vector quantity is equal to 0, mathematically we can say that vector can be represented as nothing but gradient of a scalar function phi. Okay, so we are using the gradient of scalar function phi over here to define this velocity vector v. So my individual component u will be del phi by del x, v will be del phi by del y, and w will be del phi by del z. So now one advantage of a potential function over the stream function is that in this case we are having all three variable u, v, w are accounted into a single scalar function phi, and at the same point of time it can be employed for three-dimensional flow situation. Okay, so one typical substitution if we do in our continuity equation, we will be finding that my continuity equation will be nothing but, if I substitute u, v, w, I'll be finding that my continuity equation will be becoming will be taking the form of Laplacian of phi. Okay, so with this now I will like to take up a typical flow situation, a typical phenomenon, fluid flow phenomenon, and we will try to solve our governing equation for this type of flow situation, and we will try to see its solution. Okay, so what I have considered that I have a flat plate and fluid is flowing over this flat plate. Okay, so what will be happening when we are having the condition away from this flat plate? Say if we are not having any obstruction in the path of the fluid, then obviously fluid will continue to flow with its uniform velocity whatever it was having. So that particular velocity is u, and this velocity is known as free stream velocity of the fluid. Okay, now if we are placing any obstruction to this flow, because of this obstruction what will be happening, we will be finding that because of the no slip condition, close to the surface of the fluid we will be having zero velocity. Okay, and obviously far away from the surface, velocity of the fluid will be equal to free stream velocity. Okay, or I can also call it as far field velocity. But in between this plate and in the far field, we will be finding some zone where we will be having actually gradient of the velocity field. So here you can see that velocity field is actually continuously increasing as you are moving away from the surface of the plate. Okay, so that gradient will be generating because of the viscosity of the fluid medium. Okay, so because of this gradient, what will be happening, we will be having certain region close to the plate where velocity of fluid will be less in comparison to free stream velocity u. Okay, and we'll be finding a situation where our velocity of fluid will be becoming equal to that of the free stream velocity. So the point at which this happens, corresponding to that, we define some specific location, and that particular so when you will be moving away from the surface of the plate, that zone of gradient will be actually increasing, and we will be finding the length at which velocity is becoming equal to free stream velocity is actually continuously increasing along the length of the plate. Okay, if we now join the locus of all the points along the length of the plate at which our velocity is becoming equal to free stream velocity, that particular line is particularly known as boundary layer edge. Okay, so this particular point is known as boundary layer edge, and the region below this is known as our hydrodynamic boundary layer. Okay, now what we are considering that this plate is of actually infinite width in third direction. So because of that, whatever the flow situation we will be having, that will be nothing but a two-dimensional flow situation. Okay, and we have set up Cartesian coordinate system x and y in our physical phenomenon. So now what will be happening, due to the two-dimensional nature of the flow, we have to consider two-dimensional conservation of mass and conservation of momentum equations. Okay, so conservation of mass we have just seen in the previous slide. This is our conservation of mass. This is our conservation of momentum in x direction. This is our conservation of momentum in y direction. Okay, so now when we start the solution, obviously you can see that these equations are actually very complex, and even in the left hand side we are having non-linearity also involved over here. So what will be happening, and one more assumption we are considering over here, that we are actually talking about steady flow phenomenon. Steady flow phenomenon, it means there is no change in the flow parameter with the change of time. Okay, so as the time is progressing, flow parameters are remaining constant. So that's why whatever del u by del t and del v by del t term was there in our momentum equation, that we had considered equal to 0. Okay, so now if we want to solve to find out the solution of these equations, obviously it will be complicated. Though you all are mathematicians, you can find it out, but particularly for the mechanical engineers, or for the engineers who are actually studying this type of fluid flow problems, for them these equations will be looking a bit scary, and they will not be able to analytically solve or find the solution of these equations. Okay, so what we generally do, first we actually try to do some sort of order of magnitude or scaling analysis, and based on that we try to find out that what are the terms which are of relevance for the present phenomena, and we try to find out some of the terms which we can actually remove from our equation. Okay, so that will be like helping us in simplifying our flow problem. Okay, so for that, what we do initially, we go for some order of magnitude or scaling analysis. So what I am considering now, let us consider, if we have to do scaling analysis, let us consider that in the x direction, our length scale is L, where L I am considering as nothing but my total length of the plate. Okay. Then I'm considering in y direction my length scale, let us consider as delta, where delta is nothing but I have specified over here at any location x, it is called as boundary layer thickness. So this delta I have taken length scale in y direction. If I take uh, for velocity capital U, free stream velocity as the velocity scale, then what will be happening? Obviously, in vertical direction, we are not knowing about the velocity. So because of that, what will be happening? At the moment, I don't have any idea about velocity v, but with the help of scale analysis or order of magnitude analysis, we will try to identify the corresponding scaling for v. So if I substitute these scales in my continuity equation, I'll be finding that capital U by L is having order equal to that of, say, if small v I am considering at present by delta. So that order will be actually same for these two quantities. Okay. So finally, we will be finding that my V is nothing but of the order of U times delta by N. So what I have done now, I have obtained the corresponding velocity scaling for Y velocity field. Okay. Now, if I use these particular scalings for finding out the order of magnitude of different equations in our different terms in our x and y momentum equation. Okay, so if you use this particular order of magnitude analysis, so what we will be doing, x we will be replacing with L, this U we will be making equivalent to capital U. For y, we are considering delta, and for capital U by L, we are considering actually, sorry, for small v means velocity in vertical direction, we are considering U delta by L as the velocity scale. Okay. So let me just demonstrate it for a few terms. So for example, if I demonstrate it particularly for this y momentum equation. Okay. So for y momentum equation, what will be happening? In my first term, I have U, so I'll be getting U. This term, we are having V, so for V, I have scale as U delta by L, so it will be automatically becoming U square delta by L, and for X also I have L. Okay, then if I talk about order of second term I have V into V by del Y, so V into V, once again it will become U square delta square by L square, and I have del y, so that's why because of del y I'll be finding it delta. That will be equal to minus 1 by rho del P by del y. Okay, so for pressure I am not using now any scaling term, plus nu times, so this nu is nothing but equal to, it is known as mu by rho. So mu is the dynamic viscosity which we have obtained as constant of proportionality. Now for this del square V by del x square, we will be finding V as U delta by L into L square, and for second term also we will be finding U delta by L into delta. Okay, into delta square. So in the denominator I will be having nothing but a delta square. So you can see over here this delta is nothing but my thickness of boundary layer at any different locations along the length of the plate, and geometrically if we see or physically if we see, delta by L is very small in comparison to 1. So because of that, what will be happening? Wherever we are finding delta by L in our equation, everywhere our terms will be small. Okay. So in y momentum equation, almost everywhere our each and every term of the equation is actually involving delta by L. So because of that, we will be considering that all these velocity terms are actually negligible for our typical situation, whatever we have considered. So because of that, we are finding that del P by del Y is equal to 0. If del P by del Y is equal to 0 and we are having two-dimensional field, so this clearly tells that our pressure is nothing but only function of x. Okay, so pressure is not function of y. It means whatever the pressure I'll be having within the boundary layer, same value of the pressure will be there outside the boundary layer also. Okay, and pressure will be sole function of x. So because of that, our second equation is entirely gone. And if we do the substitution of order of magnitude analysis in this x momentum equation also, finally we will be finding that both the terms on left hand side are equal to 0, and in the right hand side this first term is also equal to 0. Okay, so after all these simplifications, finally sorry, I have told you wrongly. So this terms in the left hand side, these will be actually significant, and this on the right hand side, this particular term del square u by del x square will be equal to 0. Okay, so this will be coming once you are doing this type of scaling analysis, whatever I have shown for y momentum, if you do it for x momentum also. Okay. So finally, we will be finding that our simplified equation has continuity, y momentum is gone, and in the x momentum we have u del u by del x plus v del u by del y equal to v del square u by del y square plus, sorry, minus 1 by rho into dp by dx. So this is also one important term which is already there into our equation. But finally, this term will also be gone. So how it will be gone? Let us try to see. Now, whatever this simplified x momentum equation I have got, if I apply this x momentum equation, simplified x momentum equation outside the boundary layer, so what will be happening? So outside the boundary layer, you already know we are having nothing but velocity as constant u, because within the boundary layer we are having gradient of velocity. Outside that we are having no gradient of velocity, and velocity is a constant field. Okay. So here velocity is constant. So now if I apply this equation outside the boundary layer, what will be happening? This first term will be equal to 0, because outside boundary layer this u is constant, this is also constant. So left hand side is equal to 0, and this particular term del square u by del y square is also 0. So because of that, we will be finding 0 is equal to dp by dx. So it means my dp by dx outside the boundary layer is becoming equal to 0. Now we have already found that we are having del p by del y as 0 for our main equation. So because of that, pressure outside the boundary layer and inside the boundary layer is actually same. So whatever pressure we will be having outside boundary layer, same will be there inside boundary layer also. Okay. So because of that, if outside our dp by dx is 0, obviously within the boundary layer also it will be 0. Okay. So after using this substitution, I can make this term dp by dx also as equal to 0. Now you can see clearly we are having these equations, and we are having actually in this particular equation we are having order as 2. So now we require some boundary conditions in order to solve these equations. So obviously I have told you that when we are having flow over a flat plate, and if plate is stationary, so any fluid medium which is close to the surface of the plate, that will be at 0. Now in this coordinate is our y coordinate, so because of that, what will be happening? At the surface of the plate, velocity will be equal to 0 at y equal to 0. V velocity, because this is nothing but a solid plate. So if this is a solid plate, it will not allow any medium to flow through it in a direction normal to it. Okay. So because of that, normal velocity also will be equal to 0 at y equal to 0. And as we will be moving at large distance away from the surface of the fluid, our velocity will be constant. So u will be tending to free stream velocity when our y is actually approaching to infinity. So these are our boundary equations. Okay. So now what I will be doing, because this is nothing but a partial differential equation, once again finding solution will be becoming difficult. So Blasius was a scientist who have actually used one similarity parameter, eta equal to y by delta, where delta is nothing but equal to nu x by u raised to power 1 by 2. So by using this similarity parameter, he has converted this set of equations into ordinary differential equations, and once these are converted into ordinary differential equation, then obviously either by the analytical solution or by using the numerical techniques, solution for these equations can be obtained. Okay, so what we are doing, we are considering u as equal to capital U times g of eta. Okay, so if you now do some of the mathematical formulations, for example, del eta by del x, if you find del eta by del y, and if you employ over here our stream function, which is u equal to del psi by del y, v equal to minus del psi by del x, and if you replace your momentum equation, so this is our momentum equation which we have taken in our previous slide. So this momentum equation is now represented in terms of the stream function. We know that stream function is nothing but equal to psi. I can simply get integral u times dy, and u I am writing as capital U into g of eta. So if I change the limits from 0 to y to 0 to delta, because I am taking along y direction eta as my similarity parameter, so I will be finally finding that my u into delta is equal to f of eta. So basically what we are doing, we have considered that integration 0 to eta g of eta d eta equal to f of eta. So I can simply say my g of eta is nothing but equal to df divided by d eta. Okay, so this is some initial formulation we have taken. Now if we know the value of psi, obviously I can know these values of different variables, whatever we are having, del psi by del y, del square psi by del x del y, and we can substitute these into this our main equation. Okay, so after substitution, so these are the different parameters which I have obtained based on the value of psi. So once we substitute, finally we will be finding that our governing equation is actually half of f into d square f by d eta square plus d cube f by d eta cube. Okay, now what we need to do, we need to convert our boundary conditions which earlier we have taken in terms of y and uv into the corresponding form of f and eta. Okay, so at y equal to 0, eta will be equal to 0. So at eta equal to 0, we have taken that u equal to 0. Now we have already taken that u by capital U is nothing but equal to f dash eta. So because of that, I am writing at eta equal to 0, df by deta equal to 0. So it means this condition is coming from my no slip boundary condition. Then we have also considered impermeable boundary, v equal to 0 at eta equal to 0. So if I supply this condition, I will be finding that f equal to 0 at eta equal to 0, and I have considered that at far field my u will be approaching to capital U. So that's why u by capital U will be tending to 1. Now u by capital U is nothing but equal to f dash eta. So it is equal to 1 at eta approaches to infinity. Okay, so if now we solve, this is a typical ordinary differential equation. If we find out its solution for these boundary conditions, we will be finding this as our solution. So you can see, so now this is, once again I have employed the numerical solution. So g of eta I have considered as nothing but f dash eta, and h of eta I have considered as f double dash eta. Okay, so if I numerically solve it, and if I plot f of eta, g of eta, h of eta over here as a function of eta, we will be finding that f dash eta is becoming equal to 1. So this is my f dash eta. Okay, so f dash eta is becoming equal to 1, close to the value of eta 5. Okay, so when eta is nearly equal to 5, corresponding to that, we are finding that my u by capital U is actually approaching to 1. Okay, so because of that, what we can say that we are having already the formulation of eta as y by delta. Okay, and for delta also we have some relation in terms of x. So we can say that y by delta equal to 5, and if I substitute the value of delta from previous slide, which was nothing but equal to mu x by u. So for delta, I can substitute mu x by u to power 1 by 2. This equal to 5. So you can clearly see that from here we will be able to actually find out the thickness of boundary layer as function of the x. Okay. So this is like solution mathematically we are obtaining for the flow over a flat plate. Okay. So apart from that, I have included one more problem, but I think we are running out of time. So because of that, I will stop at this point, and I'll try to take up few questions if you are having any queries.